I have no doubt that all of you have seen such realistic 3D animations, for example in movies like Shrek. But what you may not have realized is that very serious mathematics plays an important role behind creation of such 3D realistic animation. Such animation are created by modeling the material, the flesh, the skin, the fat, the muscles, and controlling them by a skeleton. The skeleton, just like a real human skeleton, consists of some rigid segments, and those rigid segments are actually animated by the artist, and the skin, the flesh, etc. take shapes accordingly in the most natural way. Now this thing, how they should look most natural, that is governed by various partial differential equations that are solved numerically in order to produce such pictures. One important technique that is used for such purposes is called the finite elements method. This is, mathematically speaking, a numerical technique to solve complicated partial differential equations. It finds uses in many diverse fields other than just making realistic 3D animations. For example, it is used in things like material simulation, groundwater flow modeling, that is how water seeps through earth, and also in lots of different engineering simulations and engineering designs. Now this technique, finite elements method, is not included in our syllabus, but still we are discussing it as a motivation for something which is part of the syllabus. Finite element methods lead to enormous linear systems where the coefficient matrix is huge but sparse, in the sense there are lots of zeros in the coefficient matrix. For such cases, Gauss-Jordan elimination is not a very good way. In fact, it is a rather bad way of solving such systems of equation. Then we need other specialized techniques that we are going to learn. And it is to motivate such methods that we are doing the present discussion of one example of the finite elements method. Suppose you take a wire frame, a frame made up of wire, and dip it in a soap solution. Then a thin film of soap will cling to the frame and will assume a particular shape. We want to determine what is the natural shape for the soap film given the shape of the frame. This is an important question in physics and in architecture, where different architectural structures must be given the most natural shape in order to reduce the stress inside the material. To discuss the problem mathematically, it would help us if we set up a coordinate system. So 3 axes, x-axis, y-axis and z-axis. Then the surface may be expressed as a function. Let's call it uxy. Physics tells us that the most natural shape or the most natural function uxy will minimize the potential energy of the surface, which is given by this rather horrendous looking expression. It is pretty complicated even to compute, and to really minimize it analytically is very complicated, if not impossible in many cases. Here capital R is the domain, that is the domain of the function uxy. So the problem that we want to solve using finite elements method is to find u numerically approximately such that this quantity will be minimized. Observe that this quantity even involves the partial derivatives of u. U subscript x is the partial derivative of u with respect to x. Similarly, u subscript y is the partial derivative of u with respect to y. Whenever we handle any structure, anything inside a computer, we have to discretize it. Thus, though uxy is a continuous function, we'll have to work with a discrete version of it. It is very much like plotting a continuous curve in a computer. Though the curve is continuous and it takes infinitely many values, we actually consider only finitely many values in its domain and consider the value of the function only at those points and interpolate, say using just piecewise straight lines, to get an approximation of the continuous curve. We do a very similar thing in case of our problem also. Here, of course, it is a three-dimensional problem, so the domain itself is two-dimensional. So we take what is called a triangulation of the domain. We split up the domain into certain non-overlapping triangles. In the two-dimensional example of drawing a curve, we join the points using line segments. In this three-dimensional example, the surface has to be patched out of different planes stitched together appropriately. To make life simple, we will define certain basis functions. Now here is one basis function. Each basis function consists of one particular point of the triangular mesh raised to a height of 1. So you take the triangular mesh and you take one point of it and lift it up to a height of 1 while leaving all the other points at height 0, that is on the xy plane. This gives rise to a conical function or function like a pyramid. Such functions we will call basis functions. This example shows a basis function where the particular node that we have lifted happens to be an interior node. If we lift a node which is a boundary node, then we get an example like this. Well, we shall express our function uxy, the thing that we are looking for, as a linear combination of these basis functions, which we have called phi. So uxy will be of the form summation over j cj times phi j xy, where the summation runs over the set of all basis functions. Because each phi j is made out of various planar pieces, so will be the function uxy. Since each phi j is 1 at one particular vertex and 0 everywhere else, so observe that Cj is nothing but the value of uxy at the jth vertex. So finding uxy now boils down to finding the finitely many numbers Cj's. Once you know the Cj's, you get an approximation of uxy as summation Cj phi j x comma y. So when I call them phi j, when I call the basis functions phi j, I am labeling them with index j. Now how exactly we do the labeling is completely material so far as the mathematics goes, but in order to simplify our life later, it will help if we label them in a particular systematic order. So let's consider the triangulation. Observe that there are various nodes or vertices. The nodes or vertices of the triangles. These come in two flavors. First, those nodes where the value of uxy are unknown. In our example, these are the interior nodes. Then there are those nodes which lie on the boundary, that is on the frame. For these, we know the value of uxy because we know the position and the shape of the wireframe. Now when we number them, we will number these unknown nodes or the nodes that are interior first. So let's suppose in our case we have got 9 such nodes. So we'll number them 1, 2, 3, 4 up to 9 in any order. So here I have shown only the row major order, row by row. You can order them in any order, but first 9 must be the interior nodes. Then outside there are 16 more nodes. Those are the nodes on the frame, and we will number them starting from 10 to 25. It will also help if we number the triangles. Observe that it is a 4 by 4 grid, so there are 16 squares. Each square is split into 2 triangles, so there are 32 triangles. And we are going to label them with numbers. We may do them howsoever we like. So I will do it in this way. 1, 2, 3, 4 goes on up to 31, 32. Let us see how we can express a basis vector in terms of the different levels. As an example, consider this basis vector. Each basis vector is created by raising one of the nodes to height 1, retaining all the other nodes at height 0. In our case, this particular node happens to be node 4. Observe that this basis is 0 everywhere except on the triangles adjoining this particular node 4. In this example, there are exactly 6 such triangles. So you can understand that the formula for phi 4 will be of the form something 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 if xy happens to be in any one of these 6 triangles and 0 otherwise. It must be of that form. Also, when this xy belongs to one of these triangles, it must be a plane. That means it must be of the form alpha plus beta x plus gamma y. It has to be of that form. Now this alpha, beta and gamma, they will depend on which triangle it is in and which basis we are talking about. Thus, we have this general form where phi j is expressed in terms of the 3 coefficients alpha ij, beta ij and gamma ij, where the subscript j denotes which particular basis function we are working with, and the subscript I denotes which particular triangle we are talking about. Of course, if triangle I is not adjoining vertex j, in that case all these things are just 0. If vertex j, if node j happens to be a vertex of triangle I, then these things are going to be non-zero. But whatever the case, all these quantities, all these alphas and betas and gammas are completely known. They depend only on the way we have taken the triangles. Remember that the expression of the energy that we are supposed to minimize, that involved partial derivatives of u. And since u is a linear combination of the phi j's, we have to be able to find the partial derivatives of phi. And they are pretty easy. Except that phi being pieced out of various planar parts, where two planes meet, there you will have something like a ridge. But other than at those points, they can be differentiated partially to produce these rather simple constant expressions. And as a result, that complicated formula for energy of u now reduces to this expression. Pretty complicated. However, observe that this is a quadratic form in the CJs. Remember that it is CJs that we are trying to find. And here it involves nothing other than Cj squared and various products of Cj and Cj primes. So it's a quadratic form. Any quadratic form may be neatly written as C transpose capital M C, where the capital M is a matrix that is determined by all those known quantities alphas and betas and gammas and the areas of the TIs. By the way, when I write TI absolute value, I mean the area of the triangle TI. And when in the earlier step I wrote TI and with a degree sign I meant the interior of the triangle TI, because it is differentiable only in the interior of each triangle and not on the boundary where there is a crease. Now remember that we have got two types of vertices. The interior vertices where the CJs are unknown, and the frame vertices, the boundary vertices where the CJs are given, because we know that the soap film must cling to the frame. Now the way we had labeled the vertices, we had labeled all the interior vertices first, followed by all the boundary vertices. Accordingly, C may be split up into two parts, C1 and C2. So C1 consists of the first 9 interior vertices and C2 consists of the remaining 16 boundary vertices. Accordingly, you partition M also. Then the quadratic form may be written like this. You expand it, then it becomes somewhat, well, I will not call simpler, but you can see which part is known and which part is unknown. Our job is to minimize this with respect to C1. Remember, the M matrix is completely known in terms of those alphas, betas and gammas and the areas of TIs, etc. C2 is known because the frame position and frame shape is given to us. We do not know C1, so we have to differentiate with respect to C1. If you do that, it looks complicated, but once you do that, it turns out to be pretty simple. Anything without C1 just vanishes, and the part using C1 now just becomes a linear thing. It was a quadratic, after differentiation it becomes linear, and it becomes this simple expression. So now we can solve for C1 by just solving this linear system of equation. One may show using some linear algebra that this is consistent and also has unique solution. We are not going to go into that linear algebra. So the important thing is that finite elements method boils down to solving a system of linear equations. That's precisely what I stated right at the beginning. It might look like a very simple thing. So you just apply something like Gauss-Jordan elimination and you can solve the system. However, there is a practical problem. The problem is this system in general will be huge. In our case, you have got M, which consists of all the nodes. So there are 25 nodes. So your capital M was 25 by 25 and our M11 is 9 by 9 to the total number of interior nodes. Now in order to get reasonable accuracy, we have to employ a huge number of nodes. That is, our triangularization should be very, very fine, like in this example. So when you use a mesh which is pretty high resolution, then the number of interior nodes goes up. As a result, this matrix M11 will be huge. However, observe that the entries of M11 or the entries of M for that matter are all consisting of those alphas and betas and gammas, and alphas and betas and gammas and mostly zeros, because as I said, for every basis function the value is non-zero only for the triangles adjoining a given node, and there are only at most 6 triangles adjoining every given node. So even if you increase the number of nodes, even if you increase the resolution of the mesh, still the underlying structure remains the same. There are always at most 6 triangles adjoining any given node. As a result, this M11 matrix is very sparse. Most of the entries are 0. In fact, in each row you will have at most 6 non-zero entries. All the rest will be 0. So it is quite possible that M is of the order M11 is of the order 1 million by 1 million. Yet in every row you have only at most 6 non-zero entries. So if you want to multiply a vector by m, you do not have to do a lot of work because you just ignore the zeros. However, if you use Gauss-Jordan technique, then in the very next step, after you have done one sweeping step, many of the zeros will become non-zero. So you will not be able to take advantage of the sparse structure. And there are other very serious problems with the Gauss-Jordan elimination for such problems that we are going to discuss later. And as a result, we need some other techniques which are suitable for huge systems that are sparse. Systems where the coefficient matrix consists of many zeros. And we are going to learn one such technique in the next video.